Shanfeng Zhu. I'm from Fudan University. I would like to thank the organizer give us this chance to present our recent work on mesh index. And this is a joint work with Professor Zai and Professor Mamitsuka in UIUC and Kyoto University, respectively. We first introduce the problem a little bit. As we all know that the number of citations in Medline has increased exponentially in recent years. Actually, currently, Medline has indexed over 23 million citations. We can also say in 2014, the Medline has searched around 2.7 billion times. It's 8% up from last year. One interest point of Medline citation is almost all citations are indexed by mesh terms. And each year around 0.8 million documents are indexed into the Medline. As we all know, the mesh is very important. It not only indexes all documents in Medline, it also has indexed many books and collections in National Library of Medicine. It has also been used to do query expansion to increase the retrieval performance. And we also have did some work in mesh in document clustering by integrating mesh information. And we also know that the logic discovery using biometric text mining is a very important research topic in biometric text mining. From this, we can say automatic mesh index is a very challenging problem. And there are more than 27,000 mesh headings organized in hierarchical structure. On average, each citation has indexed around 12 and 13 mesh terms. Each year, around almost 1 million citations are indexed. According to NIM, it's around $9 to index an article. Why this problem is very challenging? Because there are several reasons. The first one is there are a large number of mesh terms. And also, some mesh terms are used very frequently, but some are very rare. For example, here, the most frequent mesh terms is humans. It has used the index for more than 800,000 times in the whole documents. And for some mesh terms, it only appears maybe a few hundred times. So this is a very challenging problem. The other problem is for each article, the number of mesh terms are also flexible. Sometimes one document has maybe 5 or 6 mesh terms, but some documents that maybe have 13 or 14 mesh terms. And there is a very interesting comparison between the Medline and the ISMB. We all know that ISMB is very important competition recently. It's used in image annotation, and Google and other very famous IT companies, they spend a lot of money and people to do this job. It has 15 million images, and there are more than 22,000 classes. But in our Medline, it has more documents and more classes, actually. Here is the normal index procedure in NIM. And firstly, they have developed a software, MTI. And then MTI used to recount some mesh terms to the index. Index will review the recommendation and select the mesh terms, and then revise what will do the review again. And finally, it will be indexed. So they develop a software MTI to help their annotated mesh terms. Actually, why we work on this topic? Because last year there is a challenge in Europe. It's called as BioXU challenge. It's for large-scale biometric semantic index competition and also for question and answer. In the first task, the organizer distribute a few thousand unclassified PubMed articles to all the participant system, and the participants need to assign merge terms to these articles in 21 hours, and then after it's allocated in the PubMed, then they will evaluate all the performance of different submissions. It consists of 3 batches, and each batch consists of 5 weeks. For example, here we give examples how many documents are provided to the participant, usually around a few thousand. And one distinctive feature of this competition is a real program, because MTI also provided their result to the competition as a baseline. Around maybe 20 teams attended this competition. And there are a few metrics to evaluate the result. One of the most important metric is macro F measure. It's a kind of combination between the macro precision and the macro recall. From here, we can say the most frequent labels will be weighted more in the evaluation. Actually, macro F is very highly correlated to example-based F measure. Both of these two measures are weighted more on the frequent labels. Anyway, here is a result of our submission. This is the last week of the batch 3. And actually, we achieved the first place in the competition. And actually, also, this is the NM official submission. We achieved around almost 10% improvement over their baseline. The second best result is from NCBI, and the third one is from a team in Greece. Anyway, this is the introduction of this problem. Here, I also will discuss the related work on large-scale mesh index. Actually, there are a lot of work on mesh index, but only very few work can really work on large-scale prediction. So this is actually the NM official method. The input is the title and abstract, and there are 2 components. One is the MetaMap index, and the other component is the PubMed-related citation. Actually, it retrieves some similar documents from the Medline. From the first component, they try to map the text into the UML concept and then restrict it to the merge terms. This is get the merge terms from the similar citations. Then the linear combination of these 2 results. And they also add some human rules to twin their result. Anyway, we found they have some of the first limitation. They don't use very advanced machine learning techniques. And the second method is MeSHLabeler. Actually, is original proposed in World Wide Web Conference. And the group in Greece, they use this method to achieve the first place in the BioXU 2013 challenge. It actually consists of 3 steps. In the first step, for each mesh heading, they train a binary classification model. And then they train another regression model to predict the number of merge headings for each citation. And finally, give a target citation. Different merge heading were ranked according to the prediction score of each classifier. And then top K is used to get the failure result. K is from the second classifier. So this is their basic flaw. Obviously, they have some other problem. One is they only use global information. They don't use similar documents. And the other problem is the prediction score from each classifier. They theoretically they are independent trained, so they should not be compared directly. And the third approach comes from the NCBI. They use learning to rank method. Each citation was deemed as a query and each image heading is a document. Then we can using the learning to rank method in information retrieval to rank the candidate merge terms with respective target citation. And the candidate merge heading come from the similar citation. So this is actually, they mainly use local information. They don't train the classifier for each merge heading. In some cases, if the document, input document, they don't have very similar citations, their result will be poor. Now we introduce the basic idea of OM method. Actually, OM method consists of two components. One is MeSHLabeler and the other one is MeSHLabeler. The main use of MeSHLabeler is to rank the candidate merge term, and MeSHLabeler is to predict the number of merge and then combine this result to get the failure result. Here is the basic workflow of MeSHLabeler. Given the target document, we first use the global classifier logistics regression. We also train the classifier for each merge heading, and then we get some kind of candidate merge heading. The other set of candidate merge heading is from similar documents. And then in the second step, we extract a lot of features for each merge heading. And then we use ranking model in the learning to rank all these merge headings and get the failure result of a ranked list of merge headings. So the basic idea is try to integrate the various diverse features from all kind of source. They should be complementary to each other, and they should be useful to distinguish the strengths of each candidate merge heading. So actually here we list the information we used. First, we also use register regression to train the classifier for each merge heading. And different from the previous method, we propose a failure level method to normalize the prediction score, and also using local information from KN. And the other point is we consider the correlation of different merge terms, because there are more than 27,000 merge terms. So this is the first time, I think this is the first time we previous study doesn't consider the correlation between merge terms. We consider it here. And also using pattern matching, we consider the merge frequency of the target journal or the similar citations. We also incorporate the result from the MTI. Anyway, one distinct features, we try to normalize the prediction score from each classifier. Here we can say, actually here there are 4 merge headings. The classifier for different merge headings, they have a different result. For example, the most frequent merge heading, humans, they have very good AUPR curve. It has the best performance. Here we also draw the threshold and precision figures. For the given threshold, actually different classifier will give the different precision. So if we directly use the score, it's unfair for some classifiers, for some merge heading. So we use the precision score as let prediction score as a threshold, and then use needs in the learning to rank model. And we also consider the merge dependence in our model. The basic idea is we calculate the statistic, the conditional probability between merge heading pairs from the whole meta line, and then we using the weighted similarity, weighted sum to get the score for the candidate merge heading. And this score comes from the global classifier, and this is the conditional probability, and this is the weighted sum. And for the MeSHLabeler, actually we also use a lot of features. The two most important features is we use the number of merge terms of the citations in the same target journal. And also we use the number of merge terms in similar articles. These two are most important. The other four are less important. Anyway, these two are most important. So because we don't have a very long time to talk about the details, so you can check the paper. Anyway, this is the most important part of our method. Here we see the result. We get the data from the challenge, and then we using the whole meta line to train the global classifier is more than 12 million. And we also train the MeSHranker using 20,000 articles and train the MeSHLabeler using 10,000. Failure test set is around 9,000. Here is the result from the single evidence. Actually, here we can say after we doing the score normalization, the macro F is increased more than 0.01. And we also found the using pattern matching to extract the merge terms. If we're using both the title and abstract, the result is better. And these two are from the MTI. Here is the result from the multi-evidence. Some interesting result is here. So we can say if we include both logistic regression global classifier and the local classifier, after we incorporate normalization, it will be increased. After we incorporate the dependence, it will increase again. And finally, after we incorporate MTI, they will get the highest result. This is for MeSHranker. And here we can say if we predict the number of merge terms, the result will be increased more. So this is the final result for our model. Anyway, another advantage of method is we only use a very moderate server. It's maybe only cost maybe $7,000 US, I think. And we train the whole the classifier around the logistic regression classifier for whole merge heading is around 5 days, and the other training time is 1 day. But in annotation, 10,000 citations is only 2 hours. And this is the take-home message. The distinct feature of our model comes from maybe 3 or 4 points. One is we use diverse evidence from global evidence, local evidence, pattern matching, dependence, and also index law from the MTI. They are complementary to each other. And also use a very low normalization score to make the score from different classes comparable, and also consider label correlation. And the other point is actually we use the MeSHLabeler to predict the number of merge heading. Talking about the future work is we can incorporate more information such as full text to make prediction. We can incorporate more methods. And also we hope in the future the NIM can use our method to do annotation. And also actually this method is generalized, can be generalized to other tasks. For example, we think we can also use this for the protein function prediction, large-scale protein function prediction. Finally, I would like to thank our students. Actually, at that time, they are only undergraduate students, and they did a great job during the competition. I also would like to thank the collaborator, Professor Zai in UIUC, Professor Mamizuka in Kyoto University, and Dr. Wang in Virginia University. And I also would like to thank Dr. Helen Paxson and Professor Hackett Shatkai for their generous help in the final version of paper preparation. Anyway, thank you very much.
Thank you very much, Shanfeng. Are there questions on the method of MeSHLabeler? Yes?
Hi. So there are new knowledge in publication every day. Mesh headings gets updated, new terms get added. So how do you foresee your training set that has to come back and retrain your method?
Each year, maybe there are only a few hundred mesh changes. So, because in our training stage, we train each mesh classifier separately. So, if you can only change some modified mesh headings, and the other part of training actually don't take too much time.
Yes, on the back. Could you speak up loud, correct?
Following on that question, what is the value of reprocessing the entire, say, PubMed or local medline, and how long would it take based on, does it extrapolate linearly from what
It is the training of a classifier is you can parallelize them because they are training each mesh heading. So you can use different. If you have a lot of server, you can do that parallelized. So that's okay, I think.
And what is the value of reprocessing the entire PubMed? Do you foresee that?
You mean in our experience, more training data will get a better result anyway.
Because you have a logistic regression as well, that you correct?
Yeah.
So you need to actually take the whole body or the whole corpus to recompute, which is actually probably one of the limitations.
Maybe the improvement is not so high if you use Intel. I mean, if you use maybe 1 billion or 2 billion documents, maybe enough. But if you want higher performance, you use
You better not to use the entire stuff. Julie?
Very interesting, and I wonder if you're in any discussion with NLM to help improve the work that we depend on.
I'm not sure. Anyway, I met some people.
Competitions are nice, but let's get it into the practice.
I met some people in last year's challenge. I think because NLM is a government institute, so they are not like an IT company. They don't have much pressure to increase the accuracy, I think.
I encourage the discussion.
I think also because both the NLM director will be changing and people are looking at optimization. It's actually quite interesting to say, since it's an $9 exercise to add the mesh term, that means if you could reduce by $2 on several million papers, that's several millions that the taxpayer pay less. So any improvement of the process, despite the fact that it's government, we know they are highly inefficient and highly chaotropic, it's actually always a gain. Every dollars and every penny counts.
Actually, we also attended challenge this year. We achieved the first place in all
In
50
50
weeks.
So you can actually do that. That's exactly what. Thank you very much for the talk.
Okay, thank you.